my name is Harry Willcox. I'm the technical manager here at Sempra, but I tend to look after quite a few of the GelSight applications. So what we have in front of us is we've got the new GelSight Modulus system. So this is the lens, effectively, and then we've got the different attachments for being able to take measurements on the internal and external. So what I wanted to do is to just show the box to start with, just to show the principle of the system, what it looks like if you were to purchase one. It's in front of me here. You can see it. Okay, so when you purchase a setup, we have the system here, which I was just holding up, the two different current standard lens sets, our calibration artifacts along the bottom, and then we have our gel pads here, which I've just nicely knocked out of their box. Underneath here, there is a cleaning kit. So if I was to take this out, we can see the cleaning kit. Then underneath this larger setup, there is a space for a laptop to be able to hold the unit. So everything comes within this belly case, similar to the previous systems. We've got a portable unit to be able to carry around the workshop. Okay. So to start things off, what I'm going to do is to just share my screen so you can see the software. And I'm just going to run through the different lenses, the reasons as to why they've been manufactured, show you some of the changes from the existing system, and then sort of answer any other questions. So I imagine that this will be about 10 to 15 minutes. And once that's done, I'll open it up to any questions. We can go from there. All right. So to start things off then, let me share my screen. Close this down. Okay, so currently I'm in the state of software, haven't got the system plugged in. So what I wanted to start to do is to show you the difference in sizing for the systems. Okay, so this is the previous smaller system that GelSight sold. So this is our Series 2 unit, and as you can see, in comparison to my hand, it's a lot larger in its size. If I was to add one of our straight lenses onto the system, this is one of our straight lenses, so I can take the covers off and screw this onto the end of the unit, so I can pop the top off here, place it into the holder and screw it in. And the system will recognize that the lens has been attached straight away and which type of lens it is. Okay, so straight away we can see the difference in size. So when we're looking at access differences, there's a huge benefit to being able to use the Modulus system. So the Modulus has a field of view of 6.6 millimeters by 5.5 millimeters on both of the lenses. Okay, and the same sort of workflow. So when I'm placing my finger on the end of the system, you can see that we're getting that depiction. So for those that might not have seen a GelSight system before, what I wanted to do is to just run you through a very quick demonstration of the system on the Modulus, just to overview how the product works. Okay, so here we have our camera on this system, we have our lens, and then we have our gel pad on the end of the system. Now, if I was to take the pad out of the 90 degree, just to show you what it looks like, how it works. So on the end of the system, there are LEDs. Okay. So what happens is the different LEDs shine at different lighting orientations around the surface. And from that data set, we're able to depict a point cloud. So nicely positioned on my laptop, there is a defect that I didn't deliberately put on, I promise. So if I place the sensor over the defect and just align it so that I've got the defect in the center, I can click capture. And the system from that button click will create me an STL file. Now from that STL file, we're able to dissect and chop to be able to understand depths, distances, and any other sort of defect characterization that we might have. So you can see in the top right corner here that the webinar scan 02 has finished, and I've got this green box surrounding it. The reason I have this green box is because I have an automatic routine running within the software. So if I double click into this defect now, you can see straight away that the system has automatically characterized the defect for me. It's given me the length, the width, the area, the volume, and the depth. And this profile is the worst case depth that is seen on the scratch. So now for me to report that, I can click this PDF button. And straight away, we have a report generated of that mark. So on the left-hand side here, this is our movable STL file. So we can zoom in to show the different features or to give a better visual of the mark. And on this side here, we've also got the image that we're able to zoom in on to show the worst case or a better field of view of the data. Every time we take a scan, we're capturing the device that's used. So I've got the L1600 lens, the device serial numbers, user, gel, and the last time it was calibrated for that sort of traceable report that you would need. Okay, and from here I'd be able to either print that off or save that onto the laptop, send that to a customer or to one of the MRO teams within the business to make a decision as to whether that defect is acceptable or not. Okay, so the reason that the GelSight Modulus system was created was to allow us more access into areas that we previously would have struggled with. So here I have a sample component. So this is a manufactured part at Sempra that we use for some of our smart fixtures. Now this part is perfect because we've got an internal area and we've also got some flat bottom pockets that we're able to go and measure and look for defects, mismatches, all of that kind of thing. Okay, so what I'm going to do is I'm going to take my straight sensor to start with. I'm going to turn off my run routine and I'm just going to go and look to see if I've got some defects inside of one of these pockets. So previously, I wouldn't have been able to measure these kind of features with a Series 2. So if I was to demonstrate the principle as to why, it's because I cannot get access into the bottom of the pocket. Okay, so it's a good example to show you as to why, or the benefits that having a modular system alongside some of the existing Series 2 systems or Mac systems, the benefits to having sort of them together. So the same principle again now, if I go into my modular scan, I can look at this in a couple of different ways. What I'm going to do is just run my defect detection. I'm going to draw a box around the sample, analyze, and then I'm just going to define the feature type that we're looking for. So I'm looking for a wider defect, analyze, and you can see it's captured the step height. Other ways that we can measure this feature is I can go and profile the data set, and you can see we've got our mark here. And then what I'm able to do is I'm able to remove the unleveling effectively of the sample. So I can draw a boundary here. You can see that we're on a slightly curved surface. And if I was to go to my second order function, it's flattening out that data set for me to be able to find the minimum to the side, which is this area here. So that mark is looking at about 36.4 microns deep across that surface area. Okay. So this is a good point to touch on the accuracy differences between the Series 2 and the Modulus. So the Series 2 system is qualified between 1 and 50 microns at 1 micron plus 4% of the expected depth. So if we were looking at a defect that was 10 microns deep, we would be at 1.4 microns of accuracy. Okay. Now there's a slight difference with the modular system in the classification of the accuracy. So as opposed to it being between 1 and 50 microns, we start the accuracy statement between 50 and 50 microns. Okay. And the accuracy statement of those levels is the same as the Series 2. So effectively, when we're looking to quantify the sort of couple of micron defects, the Modulus is probably not best fit for those defects currently. Okay, so we'd be looking between 5 and 50 microns. We are 1 micron plus 4%. Okay, so what I'm going to do now is I've got the same components, but a different area that I'm now unable to access. So this internal feature here. Okay. So what I'm going to do is I'm going to go back to my capture area, and I'm now going to place the 90-degree probe on. So I'm just going to add my pad back in, the pokey yoke system. So I just need to make sure I get it in the right way. And when that's locked in, I can start to measure. Okay. So got my pad in, so I can unscrew the modular system here. So I can unscrew the unit, and you'll notice that the system has detected that the straight lens has been removed. I can now take the covers off of this lens, place it back onto the system. I can see that it's noticed now that we have our 90-degree lens. Okay, so in real world applications, because I've taken this pad out and put it back in, I would be recalibrating the system. Okay, and I'll run through the calibration process in a second. But for this demonstration purposes, I'm just going to run through an analysis. Okay, so looking on the internal of this part, there is a mismatch on the machining, and there's also a defect. So I'm going to take 2 separate scans. So the first one being the mismatch. So I'm just placing the sensor down on the inside. We remove some of the hair that I've obviously left off. I'm at that age where my hair is starting to fall out, so it's come out on the pad. So I've just given the pad a little wipe. I can take a capture, and then if I am to analyze the other areas in this bore, and I can see that there is another defect that I'm just going to bring the sensor to, and you can see I've picked that up nicely there. Okay, so I've got 2 scans taken. So the first scan, I'm going to put the lid back on the system. For the first scan that I've measured, we can see, start to look to see whether I see this mismatch. And this is a really good example to show the difference in the orientation of the light as to what visually you can see. So as I'm clicking this button here, effectively, I'm looking at the different channels. And when we say channel, that's the different LED that is used to take our image. And it's actually quite a good thing that there's some debris on the surface, because it helps us to understand what's happening with the light. So currently, the light is coming from our, what I would define as a Z positive, or for some people, depending if you have left-hand rule, it might be your Y positive direction. Okay. Now, if I'm to move the channel, that changes the direction of where the light is pushing against the surface. So you see now that the shadow is on the left-hand side of this debris as opposed to the right. And as we roll around, you can see the effect of where the light coming from gives us a different visual. Now, the way that the system works is it takes those images, and from there we'll be able to depict the depth of the surface by the way that the light is traveling over the image. We also have other ways to be able to analyze the surface, which is color. So that applies a heat map over the surface. Obviously, that's not leveled, so you can see the uneven scan that I've taken. I've applied more pressure at the bottom than I have at the top. We've also got an optimize, so it tries to filter the data for you. And then we have something called edges. Now, edges is one of my favorite views on the system, because it tells you in a surface plot, effectively, the areas where there could be deviations. So you can see we picked up these defects that are on the surface, or they're positive, so it's debris. But then I've also got this line going through the center, which is where our machining mismatch is. Okay, so what I can do is use one of the tools in the software, draw a profile across it, and we can see the mismatch in the material. So if I level one of the sides, level the other, we can see this sort of spike step change. So to measure that mismatch, I can go to the minimum here, and I'm going to find the peak of this surface as a maximum. And you can see that there's a 7.9, this top right value here, a 7.96 micron mismatch in the material. Okay. Now, because we've got quite a nice surface finish, it's really obvious visually. You might even be able to see it if I hold it up, but that is a 7.96 micron defect. Okay. So if we jump into my second scan that we did, which is our defect on the inside, running my edges filtering, which you can see straight away, it's very, very obvious that there's a defect on the surface. So we've got the same debris that's carried across. So I need to give the pad a clean, but you can see straight away we picked up this defect here. So I can go to my profile tool, and I'm going to draw my profile across the surface. And you can see that we've got our defect. So now I'm going to do the same principle again. I'm going to level the data set out. Now I'm able to go and find the minimum point at the bottom of this channel to the maximum point on the left-hand side. So what I'm doing here is I'm effectively asking the system to look for my 0 position. So you can see on my scale on the left, there is 0. We found the maximum depth of this defect, which is 44.5. Okay. Same principle again. To report that, click this PDF button, and that will output me the data. Okay, so I've got my measured surface. I can zoom in to show the defect, and then we can report that, we'll output that as a PDF. Okay, so from an overview of the modular system, that's probably where I will leave it. One thing I will show the differences to within the calibration of the system. So I'll run through a system calibration to show you the principle. So within the kit for the existing users, the calibration artifact has changed slightly. Okay, so previously we would have individual artifacts, so 3 different artifacts within the kit. And what GelSight have done this time, which is a really nice addition, is that they've made it so we've got this slider to walk our way through the calibration routine. Okay, so what I'm going to do is I'm going to now calibrate my 90 degree, because that was deliberately within my process flow taken off of the end of it. So I'm going to show you the principle as to how we would do that. So I've got my system here. I'm going to take the existing pad that I have out, and I'm going to place a new pad in. So I can rotate the top of the unit, and by rotating, we can take the pad out. Okay, I'm just going to pop the pad out. The pad's come out. So I'm going to grab a new pad out of the box. I've got a new pad here. Now, one of the nice add-ons that GelSight have made to the system for the Modulus is the way that we add pads. So if I go to my configure settings, to device, and I add a new pad, I can take the pad that we have, hold it against a QR reader on the side, and it will notice the expiry date, the pad type, and also the serial number for that pad. And I click OK, and you can see this is a brand new pad. It's not been used yet. So I'm not now able to go back to my capture area to capture with an uncalibrated pad. I'm going to take the pad out of the box, line the pad to the pokeyoke system on the inside of the lens, which is like so. I pop that into the system, and then I lock off the unit with a twist. And what that does is it locks the pad into its location. So the pad's now secured. Okay. So I can take my artifact, and the artifact now has different attachments depending on whether you're using the 90-degree or the straight probe. So I'm using the 90-degree, but I'm going to snap this on top of my artifact, and I'm ready to go and calibrate. Okay. So the calibration detail has already been inputted into the system. So that comes with a certificate for the artifacts that we get. So I can click to calibrate. Now on the top of the unit, there is a sort of help flow. So I can take the system, place it into its holder. I'm just going to give them a clean in a second. I'll run without as we are. So, and I can now, when we're on the flat target, click scan. I take the sensor out, slide it across one position. So here, and it locks off. And now I can take my 4 BGA scans. So click scan 1. Now I can rotate the position back in, scan 2. And you can see on the right hand side, I'm getting passes, which is good. Scan 3. And lastly, on the BGA, scan 4. So we're measuring at 90-degree increments along this BGA artifact. Now, the last one, and what I would decide as the most important, is to slide across to our groove depth. So this is our calibrated groove depth with some hold positions as well. So I can bring that down onto the system, put scan, and that's our calibration process completed. Okay. So what I need to do is I just need to rerun this scan because it's not recognised my groove, which is my scan routine that I've just done. Click capture. Okay. So from here, what we would do is we would click calibrate, and we would get a calibrated value for our scan. Okay. So I'm just going to go and change. I'll be able to clean my artifact off, which would help it to get the calibrated value. But from there, we would be able to go back into our analyze section and create our scan. Okay. So from a measurement perspective and running through the system and the principle of how it works, that's sort of what I was going to run through. So what I'm going to do is I will stop sharing my screen and I will run through any questions that anyone has. And other than that, that's kind of the overview we wanted to give. All right. So I'll stop sharing. I don't know if anyone would like to add any questions into the chat if they've got any, and if not, hopefully it was good to see the system, a bit of an overview on how it works. So if any other questions do pop up, please do not hesitate to get into touch with us. But other than that, have a good rest of your day, and hopefully speak to you all soon.